Moving on to second order differential equations, the main method that we solve these is through using the characteristic equation. And unlike the other videos, I think this video is most suited for going for an example first rather than after teaching the concept in order to teach the concept better. So say we have the second order differential equation, y double prime plus 7y prime plus 6y is equal to 0. And right off the bat, we'll make the assumption that our function of y takes the form of some constant times e to the rt, where r is another constant. And for the method of solving this, I'll drop the constant since the constant will be carried over anyway, and we can just divide by it. Now, later on, of course, we'll see that this isn't that big of an assumption to make, that y is some form of an exponential function. So let's solve this then. So what's y double prime? That's just going to be r squared e to the rt. Likewise, 7y prime is going to be 7r e to the rt. And 6y, that's just going to be 6e to the rt. All is equal to 0. Now we can factor out e to the rt, and we get e to the rt times r squared plus 7r plus 6 is equal to 0. And since e to the rt will never equal to 0, we can just divide by it, and we find r squared plus 7r plus 6 equals 0. Thus we get r is equal to negative 6, and r is equal to negative 1 for our solutions for r. And so by the law of superposition, which states that we have to add together all solutions to the differential equation to get the general solution, we'll get the general solution to this differential equation will be y is equal to c1 e to the negative 6t plus c2 e to the negative t. And you might ask, well, why is there c1 and c2? Well, if you think about it, that kind of makes sense, because we're going to have two different initial conditions, y prime of 0 and y of 0. So it only makes sense that we'll have two constants, c1 and c2, to be able to solve for that. Now, as I said earlier, we're going to show why this isn't such a big assumption to make, that our y will be some form of an exponential function, and that we can solve it of this method of factoring. So the main reason for this is, say we get r squared plus 4 equals 0. Well, then we'll get r is equal to plus or minus 2i. You might be thinking, oh, what's e to the I? What's that? Well, Euler's identity states e to the ix is equal to cosine x plus I sine x. And so if we get something like e to the 2ix or e to the negative 2ix, although the negative one doesn't really matter since cosine is an even function and sine, well, that'll just come out in the constant that we multiply this all by. So we'll get the solution for this one will just then be y is equal to cosine 2x plus I sine of 2x. All of this times a constant, and this constant can be real or complex depending on whether we want the sine term or the cosine term, because if it's, say if it's imaginary, then we'll get the sine term in the real plane, which is what we're working with. If our c is real, then we'll get the cosine term, and if our c is complex, then we might be able to get both. Likewise, say we end up getting something like r squared times r plus 1 equals 0. Well, what does this r squared term correspond to? It's a r equals 0 of multiplicity 2, right? Well, if we go back to the original equation, let's draw this out. So that'll be r cubed plus r squared equals 0. And so that'll correspond to y triple prime plus y double prime is equal to 0. So what can we make it so that y triple prime plus y double prime is equal to 0? Obviously, if we ignore the r plus 1 and we're going to look for the r squared of multiplicity 0, we'll find that this corresponds to a linear term, because the second derivative of a linear term, say x plus 1 double prime is equal to 0. So in general, if we have r to the n, then we're going to have all of the x's, so we'll get constant plus x squared dot dot dot. All of these have constants, so plus c1x, c2x squared dot dot dot, all the way up to x to the n minus 1 if we have r to the n. And so the characteristic equation will encompass exponential functions, it'll encompass trig functions, and it'll encompass polynomials, which is already most of the equations that we'll encounter in differential equations.